Okay, I'm going to be doing another demo, and this time I'm going to show using a cloud node with 8 GPUs to do a simulation of a directional coupler as well as a mode solve. And I have, you may want to take a look at my previous demo where I used a remote compute node. This one, the setup here was really exactly the same, with the one exception that this time I used a cloud node. But just like before, I SSH'd in, I copied over the binary package and then untarred it and started up the utility, and then I connected to it. And I have to be a little bit careful here. I want to obscure the IP address of the cloud provider because I don't know if I'm supposed to disclose what that is, and it really is irrelevant anyway, what it is. By the way, if you don't want to use SSH, you can use some other cloud device to run something on the remote shell. But what I did want to show is, uh, this is what it's supposed to look like when you have a super powerful machine. So you can see that in the detailed status, I've selected the node, I've closed I've not expanded it, so you can't see what the IP is, but here are eight different compute devices, GPUs in parallel, and they will all be used. They will all be used by the software. So that's what you want to see if things are working right. Now, a little bit of a detail. When I created this cluster, I changed this name to cluster 0. So when I forked the non-utility cluster, it's just /cluster/cluster, which is what the Python script I'm going to use expects as the cluster. So minor detail. Okay, so unlike the previous demos, this demo is a bit more complex. And also, it's a good opportunity to demonstrate the use of the Python window. And so let's start by looking in the tutorials. And of course, you can find this online. I'm just going to extract this right here. And there's a bunch of different tutorials. The one I'm going to focus on is on the Y-junction. I'm sorry, the directional coupler. There's a Y-junction tutorial too, which you might find interesting. And okay, directional coupler. And so there are two different Python files here, and we're going to have to do a little bit of editing to set up directories and such. So first there's the core, there's the core file, and I'm just using Notepad to edit it because the Python will actually be run within the software. There's a virtual machine within TeslaMax itself. You can also choose to run your Python from an external process. So a little bit sloppy on my part. I should have used a single variable for the base directory, but it's not really a big deal just to change it. So I'm going to do that now. And part of what it does is it'll generate a GDS file with the directional coupler in it, and then re-import that. And okay, so it expects to have materials.tpro in the demo directory. Let's just open this as long as we're in this directory. I would like to open this. I don't know why it's not. Okay, here. Good. Okay. All right. So I'm just going to copy this into here. And everything will be created in this directory. Actually, I think it would overwrite. It's going to use the file mode solve, or no, DC mode solve. Yeah, okay, so it won't overwrite anything. So that's good. Yes, so I think that's everything. So let's go back to here. We have our cluster already created and ready for use. And I think I'll just save this in case we have to somehow reopen it in the cloud cluster. And now I'm going to create a Python window, and what I'm going to do is I'm going to import this thing and then use these little code snippets to do various functionality. And okay, create Python process. And the first thing I'm going to do is I'm going to change the import directory. And And yeah, this is where we want to import from. And then this code snippet, I'm just going to copy paste, Control C, Control V into my Python window here. And this is going to create a mode solve and do a mode solve and get ready for the next simulation. Actually, there's one thing I wanted to change. I had set this thing up to study TM0. Let's look at TE0, just because TM0 is a little bit messy because the bend radius is too small, but TE0 bend radius is perfect. Okay, so it hasn't done anything yet, so it was fine to change that. Now, if I changed that after I had imported that module, I would have had to go to restart Python VM. Once it imports a module, then it doesn't rescan that file. All right, so let's go. All right, so now it's running. It's created what it needs to create. The Python thing is running, as you can see. I could abort it if I wanted to, but let's not do that. I can't run further commands in this particular Python process till it's done. What I can do, though, is I can interact with the GUI. So I can see what it's created. It created a strip waveguide. Incidentally, it created a structure refinement in the Z or in the Y axis. And so we can see that through here. Yeah, the grid spacing is finer in the y-axis in this direction. And it looks like things are running. Where is the mode solve? Here we go. Okay. So we should be able to see the mode solve as it progresses in this window. Okay. So it's running. Great. I think we have our first data. Okay, here's TE0, and here's TM0. We're plotting the EX field right now, but we can change that. So let's look at the, yeah, TM0. And as you can see, okay, and I gotta be honest, like this is not a great number for 8 GPUs running a mode solve. This is something I need to work on. And in my defense, the reason I did not work on it more is look at how much progress we've already made. So a lot of times, if you're just solving for a mode once at the start of a simulation, which is what I personally prefer to do, this is going to be fine, the current runtime, but it's something that as we move into beta and release will be improved dramatically, I think, in case you are using the software in a different way where you had to do more mode solves. But for a lot of individuals, certainly anything I've done in my career, this is going to be fine. So we'll just let this process complete. And even though it's running at not as fast a speed as it should be, it's still fine. Okay. And okay. And so the first little code snippet completed. And let's just take a look around. All right. A couple things. Somehow it selected the TE0 or TM0 mode despite the fact that I wanted TE0. I don't know what happened there. I thought I had changed that. But I can just change this to TE0, which is what I wanted. And then I will download again, since both TE0 and TM0 were solved for. Anything else to look at? Yeah, I think that's it. All right, so the first phase is ready or completed. So now let's go back here, and we don't need to rerun these two Python commands. So really just this will be fine. And what this is going to do is to actually create the directional coupler simulation and then run it. And in the tutorial, you will see all the Python that does this within the directional coupler project. So you can see exactly how it went about creating the simulation and doing all the stuff that it does. Okay, and it did a bunch of matching of structures. There's a slight mismatch, so I guess there's a grid point or two off, but it's close enough. Oh dear. Uh, yes, this is something I've seen before. Okay, so we had a little hiccup here. This thing timed out. So maybe this is a good thing, actually. I can show you how to deal with this because it's quite simple. It actually did successfully create the FDTD simulation, but now the Python thing terminated early. And so for sometimes more complicated imports or what have you, I've noticed that this thing times out, and we can change the timeout to, and I don't know why 5 seconds was selected. It's way too short. I changed it in the next version, but you may be using an older version of the software. But you can just change the timeout like this. And now I'm going to go and delete this thing. It actually instantiated the simulation on the remote server. I'm just going to delete this. That's all you have to do. Simulation will be cleanly shut down and exited. And now we can rerun this whole Python thing with a new timeout. And yeah, there's some error message about a previous thing that is ignored, but you can just ignore that. And it's just going to run again, and this time not timeout. So, a little troubleshooting thing. Yeah, I guess this command took extra long because some of these things had to be imported and then mode matched or whatever. And this time it looks like no timeout, so that's good. And once again, that command was pyteslmax call.timeout. It's a static variable within the pyteslmax call module that can simply be changed. And I really don't know. I made it 5 seconds. It's way too short. But that's why the software is in alpha. Okay, I'll just leave it at that. Okay, so actually it is running. Wow. Yes. And we better look quickly because I don't think this is going to be running for very long before it's done. So 793 gigaflops per second is not a terrible number, but the H100s, 8 of them can do a lot better. It's just this simulation is basically too small. So this does not look like a guided mode at all, but that is because we are rendering the wrong component. So we launched the TE0 mode, and we are operating in such a way where the Z is the direction of propagation. So let's take a look at EX. I think we are not looking at EX right now. What are we looking at? We're looking at EY. Okay, so that's the problem. Okay, yeah, and EX is looking quite reasonable. Now, as we go around this bend, it's going to rotate and maybe not be the best thing to look. It's not a terrible thing to look at. The better thing is probably HY. So I'll do that now. A known issue, by the way, is that the caption does not work properly for H. So yeah, it's showing something for the E fields. I don't know why it does that. It's on my to-do list. Generally, though, I would say it's better to use simulation units for most things. For these linear systems that you typically study, it doesn't much matter. It's mainly about coupling coefficients and such, which are just a function of simulation units. So, okay, so this thing is rapidly progressing through here. The directional coupler, how long have we been running? Really just a couple minutes. And again, we're not really exercising the machine at anything to near its full capacity. This domain is just too small. Let's look at what the domain is. Yeah, it's a 7.8 gigabyte domain. It's quite small by the standards of these CUDA machines. I don't know if you saw the memory report on the CUDA cores before, each one had 80 gigabytes, 80. So actually the full capacity of this machine is 640 gigabytes for FTTD domains. And yeah, you probably couldn't use exactly a 640. You can get close, 500, 550. So this is about a little bit over, somewhere between 1 or 2% of the full memory capacity of this machine. So it's not a surprise it's not scaling all that well, but it's not terrible. And for this simulation, it'll be done quite soon. So as far as the physics that are going on, you can see the standard directional coupling thing. And there's a 90-degree phase shift, it looks like, between the two modes, which is what you would expect. And what else can I say about this simulation? Yeah, I set PML boundary conditions to be the top end. Now, if you wanted to inspect the field here more carefully, you certainly could. What you would want to do is go to stop time step, not kill, go to stop time step. And that would simply, stop the time stepping, but the fields would be available and you could interrogate them. I showed how to use the pointing surface and the field measurement surface in a previous video, but also you can simply go to a location with the field edit window and look at the actual field. I'll just do that now. Yeah, see the actual raw fields are there and you can go and simply download from a given grid point or range of grid points what the field is. You can even upload something if you'd like to any of the fields involved, whether it be structural or E or H. And if you upload some random field value to something in the middle of an FTTD simulation, I am sure it will cause a problem and be non-physical. Just in case that was a question. Yeah, so I didn't edit anything or change anything. And so normal physics is being applied. Pulse is nearing the end. And very soon we'll be able to look at our various measurement surfaces. Now, in a previous demo, I showed how you can use the plot s21 command. And in this case, we're not going to do that. In this case, I'm going to use the Python bindings to download the information and display it in a plot window. And exactly what's going on under the hood, again, can be seen in this file. It's all right here, everything you need to do this. I know it's kind of a lot. I'm just not going to really talk about it, but just, if you're interested, you can go and take a look. We're nearing the end here. Oh, one thing I think I neglected to mention in the previous demos, down here in the bottom right is a network load monitor. This is for the GUI to the cluster. And so sometimes this can be helpful if it looks like nothing's happening, but then you see that this is spiking. Then you can sort of glean that, hey, we're actually uploading some large piece of data or downloading something. And so actually it's doing something. And sometimes, because the data sets involved in this software are so large and because it's so arbitrary what you might choose to do, you can imagine there are scenarios that you might engineer where you're uploading some 10 gigabytes or downloading 10 gigabytes or what have you. And then you just need to be a bit patient and just monitor this to make sure it's not stalled. Okay, I guess the Python thing is still running, you can see from here. I'm just going to let it finish. I forget exactly how long it was supposed to run. Target time is 580 femtoseconds. Oh, okay, so we're at 540 femtoseconds, 549. So this is quite close to being done. So this Python script in the background, meantime, is simply waiting for this thing to finish with a very simple delay loop where it simply checks to see if something is done, sleeps for a bit, checks to see if something is done, and so on. So this is almost done. Okay, it has detected that time stepping is completed. So let's see what's going on with the Python thing. That error message, I think, is from the previous thing. So it didn't say anything, but the time stepping is completed. And so, okay, so actually we can run the next code snippet, and this thing just downloads and measures the results. Arguably, the best thing to do would have been to have this be part of the time stepping thing where it automatically does this at the end, but this works too. So copy paste that into there. And okay, downloaded and did a little calculation in Python, just dividing some coupling coefficients. And here we are. This is the argument, and it's not the most meaningful thing. Let's see if I can just not plot that because it's in the way. It was supposed to not plot that, and I don't know why it did. But anyway, yeah, there we go. Yeah, I mean, the phase shift between the two things, you could use that to do one thing or another, but you're going to have to use a much tighter frequency spacing. So you could use the derivative of the phase, of course, to get the group index, or the second derivative, I think with some linear combination of the first derivative to get the dispersion. Maybe I'll cover that in a future tutorial, but how do I not? Yeah. Okay, now we're just looking at the meaningful things. So this is the dB coupling to the same port, and it is actually, I should have said something about this while it was running. There isn't a lot of coupling going on in this directional coupler. So actually the coupling, the cross port coupling is pretty low. So same port coupling is negative 0.83 dB at the lower end of, or at the lower frequency end to negative 0.45 dB at the higher end of the frequency. And of course the cross coupling is lower, negative 11 dB for this. And we actually could calculate the excess loss pretty easily from this. So let's, and I hope there's some loss because there really should be some loss. So let's just say, we probably, .8355. And blanking on where log 10 is. I think it's in here. Yeah, that's where it is. Okay. So all right, so these are the tools we'll need. Okay, so the excess loss is negative 0.07 dB, or it's negative 0.0726 dB for this directional coupler, which seems reasonable. Then why don't we just look at the other end of the spectrum? And of course, this could have been done from the Python script that I had, but yeah, dBSAM was not positive, it was negative. Yeah, and the positive number here is non-physical, so obviously that's not right. Okay, and then the excess loss for the higher frequency was a bit higher. It was negative 0.118 dB. And yeah, so those are the meaningful numbers that you might want from this directional coupler simulation. And once again, if you wanted to know the time delay and the dispersion, then we'd want to look at those arguments for the modal coefficients or the modal profile, but yeah, the modal coefficients, but you'd want to take the derivative and such. And I think that covers it. So thank you for watching. That is the demo. You can find this demo stuff in the tutorials. And yeah, thank you.